Hello everybody. This is a recreation of the lecture from day one. So welcome to machine learning. We're going to start off by talking about what even is machine learning and what is AI and what kinds of stuff can it do. We're going to focus on a specific type of machine learning problem called a classification task. And you're going to learn your first machine learning model, which is called the KNearest Neighbor model. And you're not just going to learn about it, you're going to actually make one and use it to predict which digit somebody has written by hand. And some important terms that we'll introduce that will keep coming back as we look at new models, especially neural networks. The idea of what is a classifier, what's a feature vector, what is dimensionality and why is it important, what is training data, what's test data, and what's a decision boundary. Okay, so let's dive in. So I asked the class what examples of machine learning might be, like are they familiar with any applications. People raised the obvious ones, like the large language models like ChatGPT that you can converse with. People mentioned Face ID, unlocking your phone with your face. People mentioned recommender algorithms. So when Instagram or Facebook or TikTok or Amazon or YouTube or anybody makes recommendations for you. Nobody mentioned self-driving cars, but when I brought them up, everybody said, oh yes, of course. This slide is thanks to an MIT lecture just from 2 weeks ago, but I think it kind of summarizes things well. You might have heard of deep learning and machine learning and artificial intelligence. So artificial intelligence is kind of the broadest term that encompasses the other ones. And it used to mean something like enabling computers to do anything that we believe that intelligent humans can do. And originally that meant stuff like playing chess or like proving mathematical theorems, because the original AI folks thought, oh, like that's like the stuff that the most intelligent humans can do. And it turned out that those things were less hard than things that infants can do, just like recognizing what an object is, or learning language, or walking around a room without bumping into things. So now artificial intelligence is kind of the broad term that encompasses enabling robots or computers to mimic human behaviors. Then within that, more recently, machine learning is a specific approach to doing that. So rather than having programmers explicitly give instructions for how to do the things, machine learning involves algorithms where if you give the machine a whole bunch of examples, the machine can teach itself based on those examples to improve. And deep learning is a specific type of machine learning that involves neural networks, and we'll talk about that later. Today, the model we're going to learn, the KNearest Neighbor model, is here. So it's not a neural network, so it's not deep learning. But it's still a model that will improve with examples and that we can use to mimic human behaviors. Okay, so let's step back here. One of the types of problem that's a very common machine learning problem that you might want to solve is called a classification problem. Roughly, a classification problem is the problem of when you're given an input, can you assign it to one of several predetermined categories, or can you categorize it? So here's some examples. If we have a picture of a tumor or a CT scan or something, we might want to just assign it to one of two categories, malignant or benign. So that's a classification problem because we're trying to categorize or classify the input as being one of a finite number of types. The example we're going to do today is given an image of a handwritten digit, be able to say what digit is it. So here we have 10 possible output classes, or 10 possible labels, 0 through 9. A much larger example of this is if I give an image of an everyday object, could we identify what type of object it is? And so here the number of output categories is going to be much, much larger, in the thousands or tens of thousands probably. You might have seen videos on the internet of trying to teach machine learning models to play classic arcade games like Snake or like Super Mario Brothers. Usually the type of machine learning model that's used for this is called a reinforcement learning model. But you can think part of a reinforcement learning model you can still frame as a classification problem. Usually you wouldn't give it an image. You would give it some numerical data about maybe the distance of the player to major things it could interact with, as well as what types of things those are. So the distance to the enemies, the distance to this question mark block. And so given a numerical list of inputs, try and identify what would the best action be. And there's a finite number of actions. We could press up, down, left, right, A, or B. So that's still a type of classification problem. Even sort of more generally, the GPT models that you're familiar with are doing a lot of stuff, and so they're not just a simple classification problem. But what is true is that at their core, they're trying to predict the next word in a sequence. And so even though the next word isn't a label that categorizes the sequence, it's still choosing the best option of a finite number of categories. So once upon a blank, the next word there's going to be a finite number of possible next words, and there's going to be a best answer, which is time. So this slide is me trying to convince you that the idea of classification shows up in a lot of different places and is a useful thing to be able to do. You're probably interested in, okay, so yeah, what types of models are going to do the classifying? What's inside this little ML model cloud? The one that everybody's excited about these days are neural networks, and there are lots and lots of different types of neural networks. Other examples would be things like a logistic classifier, a KNearest Neighbor model, a random forest, and there are others as well. Before we start talking about how the models work, let's talk about training. So I said machine learning models teach themselves based on examples. So the first step is you have to gather lots of training examples, typically thousands to millions of examples of the type of input that you want to be able to classify. And it's important that you have correct answers as well. This is sometimes called a labeled data set or a labeled training set. So if we wanted to do medical diagnosis, we would need to have a bunch of pictures of benign tumors and a bunch of pictures of malignant tumors, along with the correct label for what they are, and you feed those into your machine learning model. Your model is going to make a prediction, and then you compare what your machine learning model actually predicted to what the right answer was. And then depending on what the learning algorithm is, the learning algorithm will have the model adjust its own internal workings so that it's more likely to get that one right the next time. So after you've done all the training, then you're ready to deploy the model, and you can ask about new cases. What about this one? And the machine learning model will make its prediction, and then you can use whatever you want. You can do whatever you want to do with that. An important thing I left out, how do you know if your model is ready? How do you know if it's good? You might have 60,000 training examples, but you don't want to just say, wow, 60,000, that sounds like it's probably enough. Let's release it to the world. You want some way of validating that your model actually works. So typically what you'd do is you'd reserve some percentage of your training data, like 15% or 20%, as your test data. And you wouldn't train on that. You're saving that so that after you've trained, you can say, all right, we think our model's good. How does it perform on these examples that it's never seen before? Because that's what it's going to have to do down here when you actually employ it in the real world. And you want to get some type of estimate of how well it's going to do before you actually release it. We'll have a lot more to say about training and test data later. A really important note here, though, is that common to all machine learning algorithms, your programmers don't have to be experts in whatever they're training the model to do. So 25 years ago, if you wanted to program medical diagnosis software, you would need to get doctors and talk to them and ask them, how do you do a medical diagnosis? Anymore, you don't actually need those content experts. If you just have enough of the right data, the machine can teach itself. So the next part that we actually did when we actually did this in class was I sent everybody to teachablemachine.withgoogle.com so that they could see what it looks like to train a classification model. In this particular example was a neural network, but there's no coding involved. All the programming is already done. It's more like you're going to decide what are the classes that you want to be able to discriminate, what are the classes you're going to classify, and then you record some data and the machine will try and classify them for you. I would definitely encourage you to check it out. It's a lot of fun. But for this video, we're just going to move on. Common to all machine learning models is the idea that the input that you're predicting or that you're using for your training has got to be a numeric vector of some kind. So whether you're trying to feed in language or pictures or something else, you have to reduce those things to a list of numbers. So this is sometimes called, forgot the order of my slides. So this vector is sometimes called a feature vector because these numbers represent features of the situation that you want to be classifying. So let's pretend, for example, that we have some information about a room and we want to be able to predict what type of room is it. You might imagine that 10 and 14 could be the dimensions of the room as measured in feet. And those would be pretty useful features. I think it would be pretty easy to categorize which type of room it was based on those features. The number of features in your vector is called the dimensionality of the vector. And that turns out to be really important for a lot of reasons that are going to come out soon. But for now, just know that term, the dimensionality of the vector. So let's think about a case that would be less helpful. So if 10 and 14 weren't the length and the width, but instead 10 was an integer representing wall color and 14 represented ceiling height. It doesn't matter how fancy your machine learning model is here. You know, it doesn't matter if you have a neural network with a lot of layers and a fancy learning algorithm. If you don't feed it information that is useful in making the discrimination you want, it doesn't matter how fancy your model is. You're never going to perform very well. And that's kind of easy to realize in this simple example. But if you have a much more complicated example, it can be very easy to fall into the trap of thinking, if my model isn't performing well enough, it must be something wrong with my model. And that's not always true. Very frequently, it's something wrong with your data. Maybe you don't have enough data. Maybe the actual features that you've chosen for your data are the wrong features. So that's a big difference or a big contrast to regular programming that it's easy to forget about. Okay, let's start now thinking about the particular machine learning model we're going to learn today, which is called the KNearest Neighbor model. Let's go back to the example. So we're still doing room classification or room type classification. Let's go back to the assumption that the first and the second numbers represent room width and room length, respectively. So you could imagine that each of these dots is a training example where we gave it a specific room width and room length, and we've trained our model using these. So just based on your own human intuition, if you were going to classify these ones, think about what would you classify them as? What about these ones down here? What about these ones over here? So this is what they actually are. All these ones that were very narrow and long were hallways. These ones were dining rooms. These two were bedrooms. These three were bathrooms. These ones over here are living rooms. And these ones over here are also hallways. Probably because whoever recorded this data, they didn't think about what does width mean and what does length mean. So maybe these were hallways going, one direction versus another direction. Anyway, as human beings, we could have guessed what a lot of these things were. For the KNearest Neighbor model, what we actually do with our training data is we just save it in a big list so that we can reference it later. An important thing to realize is that this graph, this two-dimensional space, represents all possible inputs. So where my mouse is right now, that's a possible set of room dimensions. Way over here is another set of possible room dimensions. I would call this room maybe a warehouse because it is both very long and very wide. So this space represents all the possible things that we might be asked to categorize. And that idea is going to become really important later on. So let's talk about how does a K-nearest neighbor model actually do the classification. What about this? Let's say I gave it an input that was right here. I'm going to run model.classify on a length and a width that was here. The way K-nearest neighbor works is it looks for the most. We want it to look for the most similar training example that it's seen. And the way we're going to judge similarity is distance in this two-dimensional space. So if k equals 1, what we're going to do is we're going to find the one closest point from the training data, and we're going to assume that the closest point in the space is a similar type of room. And so we're going to ask that piece of training data, what type of room were you? It was a living room. And so now we're going to predict that this one that was nearby is also a living room. All right, what about this one? What would we predict this one is for k equals 1? The closest item here is a hallway, and so we would also predict hallway. Well, what does this k mean? The k is how many of the closest neighbors are we going to use to make our prediction. So if we change k to 3, now we're going to find the 3 closest neighbors in our saved training data and do a majority vote. So now that it's 3, the 3 closest are these 3, and so the majority vote would predict that this is now a dining room, even though it's the single thing that it's closest to is a hallway. And for this particular example, I think that's probably going to be a more accurate prediction. What about this one? Here, the 3 closest examples in our training data are this green dining room, this red bedroom, and this light blue hallway, the cyan bathroom. So now there is no majority vote. In this case, we might actually want to have an output that means unknown. It means that we can't guess between the 3, and that's probably good. And so I just wanted you to realize that that can happen sometimes, and maybe we'd need to collect more data, or maybe we would just say, we refuse to answer the question. Okay, so you're almost at the programming time. Whenever you look at a machine learning model, you want to ask yourself 2 questions. One is, how does a machine learning model represent its knowledge? And another is, what's the learning algorithm? How does it adjust itself based on new examples? So for K-nearest neighbor, the knowledge type is just instances, which all that means is it just literally saves the feature vectors for future reference. And there's really no learning algorithm, it just stores them. But as we'll see as we start to do neural networks, we're going to give different answers to these questions for other machine learning models. All right, so for your actual programming assignment, instead of trying to predict room type, we're going to try and predict which digit is written. And the feature vector that we're going to give it is a very large feature vector with pixel information. So I have a whole bunch of images that are 28 pixels by 28 pixels, so 784 pixels total. They're grayscale with 0 representing black and 255 representing white. And even though humans think about them in 2 dimensions, the feature vector is going to be 1-dimensional. So we're just going to take each row and append the rows one at a time to this single long list. So if we were going to train our machine learning model, we would give it a single list of 784 numbers, and then the label here would be 8 because that's the correct answer. So what's the dimensionality of my feature vector? It is 784. So here, if I have a handwritten digit 0 and k in my K-nearest neighbor model is 3, try and say out loud in your mind, how would a K-nearest neighbor model make its prediction? Hopefully you said it's going to loop over all of the saved training examples. It's going to find the 3 that are closest in this 784 dimensional space, and then it will return whatever their most common label is. So your next question is, well, wait a minute. In 2 dimensions, it was really easy to look and see how close is a point to another point. How do you even think about that in a very large dimensional space? And the answer is the distance measure that you're used to thinking about is called the Euclidean distance measure. The Euclidean distance measure generalizes very cleanly to n dimensions. So For 2 dimensions, you might imagine difference in x's squared plus difference in y's squared, and you take the square root. That's the distance formula that you learned in high school. If you have n dimensions, for each different set of coordinates, you'll look at the difference between the coordinates and you square it. And you do that for all 784 of your coordinates and take the square root at the end. And that's the Euclidean distance in n-dimensional space. So I've already written a framework for you to look at, and you can go to the assignment and clone the framework and kind of look in it. The basic assignment, first assume that k is 1 and implement a classifier where you just base your predictions on the one closest example, because that's easier to implement and you can kind of see how it performs. The more advanced assignment, which is what I think about as kind of the A-level assignment, is generalize it so that it will work for any k value. It's a little bit tricky. I gave you, there's a reference that you can use. And test your code for different k values to see kind of what gives you the best results. There's some additional extensions that you could implement. It turns out that if your closest points aren't very close at all, you might not want to use them. That might not make sense to base your predictions on. There are other measures of similarity besides distance in n-dimensional space. There's one called cosine similarity, which measures are 2 points roughly in the same direction in the space. And sometimes that will, depending on your task, that'll give you better results. There's a couple more extensions as well. Good luck. I'll be back next time.